Hello and welcome to this next video. Here, I want us to do a quick recap of this whole process from start to finish. And I want to touch on a couple of caveats and considerations about what we have covered. So let's do this right from the top. Our transformer model takes in our sequence and tokenizes it. Each token is mapped into an embedding vector, a set of learned numbers that capture abstract features about the token and that have been learned during training. Because transformers process all tokens for a sequence in one go, the model adds positional encoding, numbers that inject information about where each token sits in the sequence. So embeddings say what the word is, position says where it is. With this positional information factored in, the sequence enters a stack of transformer blocks. Inside each block, the self-attention mechanism allows each token to share information between itself and the others. To do this, 3 new vectors are created for every token: a query, which represents what any given token is looking for in other tokens; a key, which represents what a given token has to offer other tokens; and a value, which represents the actual information that a token can pass along. By comparing queries with keys using dot products, scaling, and then softmax, the model produces attention weights, numbers that decide how strongly each token should pay attention to every other. These weights are then used to blend the value scores, again with the use of matrix multiplication, producing new context-enriched vectors for each token. It is these enriched tokens that flow into a feed-forward neural network, which applies non-linear transformations to refine meaning even further, capturing patterns like tone, intent, or if X and Y appear together, they mean Z. And this dance of self-attention where information is mixed across tokens, and the feed-forward network where context is refined further, layer after layer, gradually builds up a deeper and deeper understanding of context. With the data having passed through a series of these transformer blocks, we move on to the final part of the process, inference or prediction. Here, the model only needs the last token's vector. For our example, that was corporate. That vector is passed through a linear layer that projects it back up into the full vocabulary space, producing one score for every possible next token. To ensure that all values are positive, we exponentiate them, and then we apply the softmax function to convert the scores into probabilities. The model can then use this information to pick the most likely next token for the sequence. So for me, at least, I think that's really useful to do, to run through it at a high level like that from start to finish. It can really tie it all together as we've gone into some depth over the past few videos. Now, on top of this, I wanted to run through a couple of caveats or extra information about this process. The first is just to reiterate that we were really just using toy numbers for our examples. In GPT-esque models, it's not 5-dimension vectors across a handful of tokens. We're talking vectors with over 12,000 dimensions and vocabularies with over 50,000 unique tokens. Also, in our example, we passed in the sequence, she packed her bags for the corporate, a total of 7 tokens. This set of tokens is what is known as the context window. In other words, the volume of tokens that the model can look at to derive the context for the next token. In reality, the context window can be in the tens of thousands of tokens, sometimes even over 100,000 tokens. Keep in mind, however, this context isn't just what the user puts into their prompt. It can be made up of all the instructions that tell a model what its role is, what it should do in certain scenarios, what it should never say, and so on, details known as the system prompt. On top of this, the context window can contain all of the memory of the back and forth conversation that you've already had with the model prior to this point, so you can see how it all does add up. The user prompt, she packed her bags for the corporate, would come after all of that other information when the model is deciding and figuring out what token should come next. Cool, so that was that. Next, I want to talk about something called multi-head attention or multi-head self-attention, because this is technically what is being used in the architectures of these models in practice. Now, when we ran through self-attention, we described it like this. We had our token vectors coming from the positional encoding, and then for the attention scores to be calculated, 3 new vectors were created for each token: a query vector, a key vector, and a value vector. And the difference between these was that each used a different set of weights in the calculation process. The output of all of this was the context-enriched vector for each token. Now, before we get on to what multi-head attention is and why it's different to this, I also want to point out one thing that I glossed over to keep things simple. At this point where we have our context-enriched vector, there is actually another set of weights that are applied to ensure it is projected back to its original dimensions. So here on screen we started with a 5-dimensional vector for a given token. We would want to continue with those dimensions going forward. Anyway, I did just want to mention that, but at the overall level, what we are discussing and showing here is one process, one set of weights for each new vector, and one vector being output for each token. This is a single head of attention. In multi-head attention, we would start the same, so the same token vector coming into the self-attention layer, but instead of just one set of weights for each query, key, and value, we could have multiple sets of weights all being applied in parallel. These unique sets of weights are applied to the input vector, creating many different context-enriched token vectors. And the reason for this is that it's been found that this can essentially split out the learning, and thus meaning can be derived more deeply across different views. In the example on screen, we have 3 unique sets of weights for each query, key, and value, and so we would say we have 3 attention heads. Each of these heads would naturally find its way towards its own abstract understanding. So perhaps head 1 might focus on order and grammar, head 2 might highlight topic and tone, and head 3 might lock onto some other part of language such as adjectives or verbs. In a GPT type model, there could be upward of 96 of these heads in each attention block. Anyway, the output vectors in this process are concatenated, and then just like we talked about a moment ago with a single head, another set of weights is used to project this back to the original dimensions. So that is multi-head attention and how it differs from what we discussed in the earlier tutorial. Awesome. So the last thing that I wanted to cover off is how a model like this is trained. So if we head back to our architecture diagram, you'll remember that as we learned about all of these different parts, we discussed that there is a huge amount of weights and parameters throughout. At the start of the training process, these are all random and they need to be learned and refined. So when millions and millions of sequences are fed through, for example, the cat ate the mouse because this is training data from real text that already exists, we know that the next word in that sequence is hungry. In the early stages of training with random weights, the model isn't going to be very good at predicting this, so we may get a probability distribution for the next token that looks like this. Now, the exact word that has the highest probability is not of great importance here. What really matters is the probability of the correct token, so the token hungry in this case. We know it's the correct word, and therefore our expected probability for this word is 100%. As our model predicted only 5% chance for the token hungry, this isn't very good. It's quite a high level of error. To be more specific, to measure this error or loss, we use cross-entropy loss, which you can see the formula for on screen. All we need to do is plug in our predicted probability, so 0.05, and you can see this results in cross-entropy loss of 2.9957. This is quite a high loss value, and because of this, when the process of back propagation takes place, the optimizer will make bigger adjustments to the weights and parameters throughout the architecture. As we know from the deep learning section, this process continues for each batch of data that's passed through, and eventually the model starts to learn what weights work best to minimize that loss value. So let's say after many iterations of training, our model is now predicting like this. As the difference between the expected probability and the predicted probability is now much smaller, we can see the loss value decrease, and thus when backpropagation is applied this time, the changes to weights will be much more subtle as they are getting nearer and nearer to the optimal values. Once training is finished, so when the cross-entropy loss across many input sequences is as low as it can be, the model object can be saved. In other words, the weight matrices for the embedding layer, those for queries, keys, and values in the attention layer, as well as those in the feed-forward network, are all frozen to be used whenever new text comes in for prediction. So there you go, a quick high-level overview of the end-to-end process, and then a few caveats and extra learnings that might be useful and interesting. Now, something really important to remember, unless you are going to go and build your own transformer, which, to be honest, most of us are not, we don't need to know all of this sort of stuff back to front. But I think it's really important to understand before we move on to other concepts and tools surrounding these incredible models, their applications, and how to get the most out of them. With that said, it has been awesome running through all of this with you. I cannot wait to keep pushing forward. So I will see you in the next tutorial.